So we are starting our fifth and final learning objective for this course, event-based architectures. We've come a long way. Let's do a really quick recap. We did program execution. This was partially the introduction to Scala learning objective, but we also talked about how programs are executed a bit. We talked about the heap and stack mostly, and pass by reference were our two big topics. How are values stored in memory, and how, when we have objects on the heap, how are those references affecting the functionality of our programs? We looked at our pair of paradigms, object-oriented programming and functional programming. Here are two different ways of approaching the structure of a project to be able to accomplish the goals that we want. These are different ways of organizing our code, different ways of reusing our code, and they had pros and cons to both of them. And with both of these, as you are well aware, I forced you into using the paradigm that we were talking about at the time by enforcing restrictions. We removed all those restrictions when we moved to data structures and algorithms, which seem to just come and go really fast. I don't know about y'all, but data structures and algorithms seem to just be a blip. We're all distracted with this transition to online only. It just came and went like crazy. But we talked about different data structures, linked lists, which we were talking about all semester, and using it as kind of a black box, just as something that works. We cracked that thing open and saw what was inside and how that was structured. And then we used that knowledge to talk about trees and graphs, two new data structures that represent information in ways that we haven't seen before. The information we put in trees and graphs wouldn't quite work in a raw linked list or a raw array for that data that we're seeing. We talked about algorithms to work with those. Now, finally, event-based architectures. There's been some motivating context earlier in the semester for these, especially during functional programming, where we talked about what happens when two pieces of code need to access the same information at the same time, or more importantly, what happens when they write to the same information at the same spot in memory at the same time. And we talked about immutability. Well, let's just not allow that and then not have that question. But we never really talked about how do we have two pieces of code access writing to the same spot in memory at the same time. How do we even get to that situation? That's what we want to talk about with event-based architectures. Thank you, Ruslana. There's a lot of conversation that has nothing to do with lecture. So how do we even have two pieces of code running at the same time? Or even why would we want two pieces of code running at the same time? So let's talk about how we're going to do that and what that means. And this is something that wouldn't really be a topic of conversation even like 10 years ago or so. But this is something that we're seeing in the industry and just in the world of computers in general that has this becoming an ever-increasing topic to discuss. And it's why now, even in a second semester course, we're talking about these event-based architectures, or more importantly, concurrent programming, where we have two pieces of code running at the same time. And this is becoming an issue, or I shouldn't say an issue, but a feature, because everything's getting bigger. I don't know if that's how I want to lead into this, but our processors aren't really getting faster. There's a limit where our processors are sticking around the single-digit gigahertz, usually under like 5 gigahertz, and you don't see processors getting faster than that. Processors used to keep getting faster and faster. I remember the days of kilohertz and megahertz processors. If you had like a 3 megahertz processor, that was a big deal, and then we started getting hundreds of megahertz. It was a huge deal. But we've been pretty stagnant at single-digit gigahertz. And there are limitations that are not really allowing technology to efficiently proceed beyond that, at least not for commercial products. But what we are seeing is getting more cores. We have these quad cores and 8 cores. We have lots of cores. And if you have a GPU, you might have thousands of cores, of processing cores, of CPUs inside your processor. So, and this is the direction that the industry is going, is having more cores instead of having faster processors. So to really take advantage of those cores, we would need multiple things happening at the same time, so we can use two cores at the same time. If we have two pieces of code running at the same time, we can run each one of those on a separate core. And then, no sound. That might be a you issue. I think chat would be blown up if there's no sound. This morning I actually had my mic muted for like 5 minutes during Q&A, and yeah, chat blows up. Chat does rightfully blow up during that. So to be able to take advantage of those multiple cores, we want multiple things running at the same time. And then when our apps get large enough to not be able to be contained on a single machine, then we're distributing those across multiple machines and having multiple processors even running at the same time. Not just multiple cores in the same processor, but multiple machines, multiple heap and stack, like multiple RAMs. Everything's completely duplicated. So we have to have multiple things happening at the same time. And we'll specifically be talking about concurrency in this class. So one of those things we won't get, which LinoX is pointing out, parallel processing. We're going to talk about concurrency, where two things are happening at the same time. To get parallel, I might be blanking on my vocab. To get real parallel, maybe it is parallel processing. To get real parallelism, I know at least that's one of the terms that they use. To get true parallelism, there's an extra layer on top of that, on top of the definition of concurrency. Concurrency is just two things happening at the same time. Parallelism is where you take the fact that multiple things are happening at the same time to write more efficient algorithms that take advantage of that concurrency. We're not going to talk about the algorithms that can distribute stuff like MapReduce, that are actually going to take advantage of the multiple cores to be able to increase sometimes even the I shouldn't say asymptotic runtime, but actually decrease the runtime of your algorithms. But we're not going to talk about the efficiency parts. But we will talk about how to have two things happening at the same time. And this is very important for web apps, for example. If you have two users on your site, you better have some concurrency built in, because you want two people to be able to use your site at the same time. So with the rise of the internet and networking, and this transition to more cores instead of faster processors, these are two huge reasons why concurrency is becoming an ever increasing topic. This is just something that these days, it's a topic that you are going to run into. It's something that we do have to understand, at least at some level, to be able to really be able to function these days as a developer. So let's talk about how we do this. All right, let me just open it this way. So let's talk about how we're going to do this in Scala and how we're going to do this in this class. At the same time, processing is the technical term. Thank you, Mike. Can you read the objective and explain little each part? I don't know what you're talking about, but if you're talking about the homework, that's a Q&A question. That has nothing to do with what I'm talking about right now. Try to keep the lecture questions, the lecture chat, actually related to lecture. I'm not going to stop lecture and go on a tangent. I mean, I might, but I don't intend to. So to that end, we want to write an actor. Oh, yeah, that question I can't answer. All right, sorry for that. Yeah, each of the 3 bullet points. Yeah, sorry about that. I misunderstood what you're saying. So this is broken into really 2. So event-based architectures, that's how we're going to get concurrent code. We're going to talk about 2 ways that we're going to build event-based architectures, and it's going to split the 2 weeks evenly. This week, we're going to talk about Scala's and the Akka library's actor system and talk about all of that. Next week, we're going to be talking about WebSockets and how WebSockets apply the event-based architecture to get concurrency running. And the third bullet point, this is just kind of an overarching, kind of an umbrella term that's covering the entire 2 weeks. You should be able to trace through the execution of these. This is what the lab's going to be about, and this is what the lecture questions and the homeworks will be about. So for the lecture questions, write software using actors for these first 3 lecture questions. Next week, write software using WebSockets for the next 3. And then for the lab activity, I'm going to give you code. Here's a program that uses actors. Here's a program that uses WebSockets. Talk me through what's going on here. Talk me through what this does. So the actor system, this is how we're going to get concurrency in ACA or in Scala. So write a Scala program that has concurrency, and then we're going to use WebSockets to write a web app in Scala using these event-based ideas. So these are 2 different things. John Boy, we can talk about that at some other point, but I appreciate your apology. So let's go back to our. But right now I got to focus on lecture. So let's go to. So with that, let's go to what we're going to learn today. Today, this is our goal of today, is just getting an actor up and running. What are actors? What is concurrent code? What's event-based architectures? We really just want to get the groundwork here, so the lecture question isn't too involved, but it does walk you through it is going to make you go through the process of just setting up your first concurrent program. For this, we're going to write, or not even a program. We're not even getting the whole part of it yet, unless you do your own testing, but I'm not requiring testing on this one. Wednesday we will. Wednesday will be about how do we test code that runs concurrently. Anyway, I'm getting ahead of myself. Write a string actor class that's going to take in its constructor just a string. That's going to be its initial value that it stores, or which will be a variable. And it's going to react to 3 different events, which in the world of actors, this is going to be in the form of messages. 3 different message types that it can react to. The append message, which has a string in its message, and your actor, when it receives a message of type append, it'll append that value to the end of whatever value it's currently storing, which was initialized by the constructor and then grows with append. The get value message, and whenever it gets a get value message, it's going to return with a value message containing the string of its current value. So we're just building some basic I/O structure. And most importantly, as I mentioned, just setting up an actor class. Setting up a class that's going to run concurrently. I already mentioned all that as I was walking through. So with that, what are we talking about? What's concurrency? And what are we doing? So let's start with the ground floor definition. Concurrency, I've been saying this word quite a bit. This is where we have multiple things happening at the same time, which is in contrast to what we've done so far. Most of what we've seen, what we've done, what all the assignments are in 115, 116 are what we call sequential programs. This is where our code executes one statement at a time, and they execute in the order in which they're written. And if we want to change that order, if we want some anything dynamic in that order at runtime, we would use control flow to do that. We'd have our if this Boolean expression, then run this code, else run this code. In 115, we saw the flowcharts where we have some decision. An if is that diamond, which has the conditional. Then we branch based on the decision there. Then we had the loops. We have loops that'll continuously run a line of code until a condition is false. So we had ways of changing the order and changing the structure of our code. It's not strictly just start at the top and run each line one at a time, but we only had one piece of code running at the same time. So what if we want multiple pieces of code running at the same time? Instead of saying conditional, if true, run this, else run this. What if we want to say run both of these both at the same time? And that's what we'll get with concurrency. Why would we want to do this? Should be a question on your mind. I gave a few motivating things when I was at the course website. But let's talk about this a little bit more and give a little more context that you can relate to. In 116 and 115, we've seen concurrent code. You've actually come near. You've been working with concurrent code. We just don't shine a spotlight on it. We kind of just pass it off as, that's something that happened. Don't worry about it. Now we want to worry about it. We want to talk about it. So the 2 types we had were Web servers in 115. If you have two users visiting your site at the same time, your site should be able to Your site should be able to handle that. And I should go back and double check if Battle is concurrent. It's possible that it is handling one request at a time, but it's certainly possible that it's running concurrently. We're going to pretend that it's running concurrently for the sake of my example here. At the very least, there's probably a setting where you can just make it run concurrently. Anyway, if two users visit your site at the same exact time, you want both of those users to be able to see your page. So at the very least, actually, I'll backtrack a little bit on that. Battle is running concurrently. So at the very least, when your server, you're running code that's handling a request from one user, and at that time, another user requests your site, sends a GET request, HTTP GET request to your index.html. When that request comes in, your code has to be listening for that. So if that request comes in and your code is off processing some other requests, getting your index.html ready and sending it in a response, you still want to queue up that request that you're getting. You want some queue of things that you need to handle. So you have part of your code which is listening for new requests and part of your code handling the current request that's being executed. So at the very least, you have to maintain that queue. So at some level, Battle has to have some concurrency to be able to do that, or else you can't guarantee that you can support two users, which is an awful feature to have for a web app. If your web app only handles one user, I'd say you don't even have a web app at that point. Can we really call it a web app at that point? So what we did for this was you provided callbacks. It was actually annotations on your Python methods. You would say this Python method should be called whenever I get a request for this path. And then the server handled it from there. When it got the event of an HTTP request, it would call your code. So we had an event-based architecture. You said, when I get requests for this path, run this code. When I get requests for this path, run this code, etc. And then whenever any one of those events occurred, your code would be ran, and your code could be ran concurrently, and that would be handled at the server level. Battle would handle that. And at the very least, Battle is handling that queue of how to process these requests if it's not fully concurrent. I should crack open that library someday and have more concrete answers than that. But at some level, there's concurrency happening, and you just give it the callbacks and say, call these functions when appropriate. In 116, we'll talk about GUIs in a few weeks. I'll only have one lecture, and we'll just kind of talk about how those homework assignments built those GUIs. But I don't have an assignment on it, so I'm not going to take too much time if it's just a one-off lecture. But in each homework assignment, you did see a GUI. GUIs, by definition, have to be concurrent. These GUIs are running some code. They're doing some logic. They're running your code at some level. They're updating the display at the very least. For Jumper, this was very clear. There was a game loop, an update loop running at 60 frames per second and calling your update world method 60 times every second to update the game. While the code is doing that, it has to also listen for user inputs. So as the user is interacting with the GUI, which is the point of the GUI, those user interactions have to be listened for by some part of your code. So your code has two things that it needs to do at the same time: updating the physics and also listening for user inputs. So how do we do two things at the same time? This is a clear case where we absolutely have to do two things at the same time. We can't have our entire program just sitting in an infinite loop checking for user inputs. That's not going to work for us. So what we do instead is have our GUI listen for the events of the user inputs, listen for the mouse clicked event, listen for a key pressed event, and then react to those events by calling some callback code. So for this, we have listener classes that override a method that's called whenever one of those events occur. So we'll have if we have a button on a GUI, we're going to give that button a listener which has code that's going to be ran when the button is clicked. So we have an on-click event, and then we have some code that's going to be ran concurrently when that event occurs. And we have some concurrent loop that's going to listen for any events that are occurring. That's happening while our model of our app is doing whatever it needs to do to be able to run the actual program. So we have multiple things happening at the same time. We have a need for something that can handle that. And that's going to be concurrent code. And we're going to accomplish that in both of these cases with event-based architectures. We have, instead of writing a main method, run this line, then this line, then this line, then this line. Instead, we're going to say, okay, when this event occurs, run this code. When this event occurs, run this code. When this event occurs, run this code. Those events can be mouse clicks. They can be HTTP requests. They can be messages that are sent between pieces of code, as we'll see today. They can be any type of event, but we have this general model of when an event occurs, run some predefined code. And multiple events can be triggered at the same time. Multiple pieces of code can be reacting to events at the same time. And an event can trigger multiple pieces of code to execute. So we might have an event that has multiple listeners to it that are going to react to that input, which are all going to execute at the same time. We might have two functions that we want to run whenever the mouse is clicked, for example. Both of those will run effectively at the same time. Usually not exactly at the same time, but from our perspective, from the human developer perspective and the user perspective, they're happening at the same time. So when we've seen these before with GUIs, with web servers, with Bottle, we hid all the details. All the concurrency was in that library itself. Then we provided the callback functions, and then the library called our functions whenever appropriate. So we want to crack that open and see how we could do something like that. And of course, we're still going to use a library for the concurrency. We're not going to be creating our own threads and things like that in this class. But we will go another layer down and see what was going on, at least one more layer deep. So the library we're going to use is the ACA library. This is already in the pom.xml for the examples repo, so if you just want to pull it from there, that's fine. But the ACA library is what we'll be using if you want to go to their website. It should be linked. I didn't double check, but it should be linked from the course website. I didn't double check today, but I'm sure it's there. I don't know why it wouldn't. It should be linked from the course website. So you can check out the documentation for the library itself. There's all kinds of good stuff in there. ACA does a lot more than just actors too. There's all kinds of good stuff in this library. And it's based on this actor model. So we want to talk about what actors are and how they enable concurrency. That is linked. Good. And how they enable concurrency in event-based architectures. So each actor object, I say the sentence doesn't quite make sense on a technical level. It bugs me. I don't know if it bugs you, but we're going to instantiate actors of types defined by classes. But we're going to have these actor objects that are going to run concurrently in our programs and react to events. And we're going to see those events are messages in this actor model. So actors are going to pass messages to each other. So for example, if we have two pieces of code running at the same time, they're both running concurrently. What if they need to share some information? What if they need to communicate with each other, but they don't share all of the references that each other have? You can't say this actor go to other actor dot. Actually, you could set that up, but let me bail on that one. But if they need to share information, if they need to communicate with each other, we're going to use a message passing system that's built into this ACA library. They're going to send messages to each other, and those messages can contain any of the data that they want to share. So they're going to pass messages to each other to be able to communicate and then react to those messages by calling some callback code, which won't necessarily be functions. Well, it doesn't matter though. You could think of them as functions, I suppose. And these messages are case classes or case objects, which we'll talk about and define in a few slides. So this is an event-based architecture. These actors are going to work based on message passing. These messages that they pass are events. So receiving a message is an event, and we're going to write code that executes whenever that event occurs. So this is where we're getting our event-based architecture, which is our common theme throughout these 2 weeks, whether we're talking about actors or WebSockets. The event-based architecture is the common theme. We have an event that can be triggered. We execute code whenever that event triggers, and then we can trigger events or send messages, in this case, in the actor case, to be able to cause that code to run. So let's talk about case classes and case objects. These are a different type of class and object in Scala with simplified characteristics that are usually used just to store a small piece of data or any data without having any real functionality. At least in our cases, I think technically you can, but I don't know why you would. But in our cases, we won't write any methods in these classes or objects. We're only going to create values and variables. I guess it doesn't make sense for them to be variables either. But and we're not going to have any values or variables that are created outside of the constructor. So these classes are only going to have a constructor and just have values in that constructor. And that's it. When we use a case class, one of the big differences from just using a regular class, because you could do that with just a regular class and only define a constructor, one of the big things that we get is all the values are actually, the references are actually compared by value and not by reference. So if you have two objects of some case class type, and you say, are these two equal, using equal, Scala is actually going to go through, instead of just saying, do they refer to the same object, it'll go to the objects that those two references refer to, look at every value defined in its constructor, and check if every value is actually the same. So it'll call equals on each value defined, each state variable, or state variable, that term is getting outdated because these are values. But if each value is the same, then that's going to return true. So we get better ways of comparing these things. Is one of the big features that we'll end up using for case classes and case objects, or for case classes rather. A case object, so in essence it has an overridden .equals method that checks the values of each of the constructor parameters. A case object is the same as a case class, except there's no constructor. This is when you just want to signal that some event has occurred, and you don't need to communicate any information along with that event. So it's just, this event happened, deal with it however you deal with it. Where a case class, you would create objects of this type to be able to send some information, to communicate some information to another piece of code. So here's two examples. We can have a case class by equipment, where it just has some constructor parameters. In this case, just one, an equipment ID as a string. And this is part of the yet to be released, but part of the clicker assignment. If you have an event where a user is trying to purchase a piece of equipment, we're going to get this event, and we want to handle that in some way. So whenever we receive an object of type by equipment, we're going to look at that equipment ID and say, okay, an event just occurred. The user is trying to purchase an equipment with this ID. Let's process this as appropriate. A case object just isn't going to have any constructor, not communicate any information. So this message would be sent when we want to initialize the game, in this case, a setup object. When I receive a message of type setup, I'm going to set up the game. I'm going to do the initial whatever is necessary for that. And that's exactly how we define these. So case object, case class, we're going to put them right in our code like we're defining any other object or class. Except we typically don't create a whole new file for each one of these because we'd have a lot of one-line files. So we can create them right above our class. Typically is something you can do. In some of the homework, the handout codes, I'll create one extra file with all of the case classes and objects in them, just for organizational sake. So once we have our case classes and objects, we're finally ready to talk about actors. Let's set up our first actor and react to some events and build our first event-based architecture style program. Those are all words, but I don't know if they made sense together. Anyway, so to create an actor class, we're going to extend actor, which comes from the ACA library. That's going to give us all of the concurrent functionality, all of the everything that we need for this thing to behave like an actor in an actor system that we'll see in a little bit, how to actually create instances of these, which is not as simple as saying new my actor. We'll talk about that. So we're going to extend actor. That gives us all kinds of functionality and all kinds of architecture. The one thing that we're responsible for is overriding, or rather defining. Yeah, I never thought about that. But overriding this receive method, since it's abstract, we don't need the keyword override. I just gotta check one thing real quick, just to make sure I'm not going insane. I had to check that in IntelliJ. We don't need the keyword override because this is an abstract method in the base class, so we can omit the override method, or the override keyword. But we can add it there. That's what I was checking. You can add it there and it's fine. But we usually don't in this case because, I don't know, the documentation doesn't. So I didn't really think about it. It's a horrible lesson. Don't listen to that. I will say not to do that. You'll hear me say that a lot. So we want to override this receive method that takes no parameters and returns this receive, which is going to be built with the cases here. And we're going to say, how does this actor react to each message type that it's coded to react to? So here I have two message types, custom message type as an object. So I'm going to use the case keywords, have this big case statement, and say if the message type is a custom message type object, then run this code. And this is in the syntax of our functions. When this is the input type, run this code. And we can add parentheses here if we want multiple lines. But whatever we type here, whatever code we type here, is the code that's going to be executed every time we receive a message of type custom message type of this object. Whenever we receive a message of type another message type, beautiful names that I wrote here, another message type, which is a class with some information in it, whenever we receive something of this type, run this code. But this time we want to give this message that we receive a variable name. Since this is a class, we want to be able to get the information out of it. So we're going to give it a name along with the type, where the object we just had to give it a type. We want a name and an object so we can get that information out of that message type. So we have this variable of type message. I want to get that value out of there. I can get it using this syntax. So give the message a name and then access its variables or values. I'm using those interchangeably here. Access its information, I'll say. Access its information by accessing those names that you used in the constructor of that class. Now we can get that information and handle it however we handle it by giving this code block. If it's a one-liner, we can use this syntax. If it's multiple lines, if we want more room to work, we could add braces here and define a whole code block with that syntax. But this is our basic structure. We imported the library, we extended actor, we override receive, and we say on each message type, or for each event that can occur in our event nomenclature, or in our event vocabulary, for each event that can occur or each message type that we can receive, do something based on that message being received. And this is how we can get our event-based architecture using actors. So that's the main core of what we're doing. Now let's just start. Now let's see some implications and applications of that. Oh, wait, actually we have one more thing. The how to actually run this thing. The keyword case is basically a type check. And we saw this very briefly earlier in the semester when we overrode the equals method. We would say if the type is the same type of this class, check if it's equal. Otherwise, don't do anything. We used case We use this syntax: case if it's the same type, give it a name and check the values that we want to check. And then case underscore, return false. So we did see this very briefly earlier, but yeah, it's checking the types. Before we saw this in a match statement, and we would check the types and do something different based on the type of the variable. So yeah, we're doing something different based on that. So yeah, it's basically a type check. And I got ahead of my slide here. Let me just click through this. And then the last piece of this, actually using this actor in a class, in a program. So how I have this actor class. How do I actually run this thing then in a full program? How do I actually run that and actually take advantage of the concurrency? So yeah, the case is checking the type, and then if the type matches the type we have here, then that's the code that's executed. So when this receives a message of type another message type, we're going to check, okay, is this of type custom message type? No, so don't do that. Is this of type another message type? Yes. So name it received, or store the reference to that message in a variable named received, and then execute this code over here. So yeah, we're checking the type using the case keyword. Yeah, exactly. It's like a switch in Python, except it is doing type checking, not just value checking. So we're going to create this actor using this syntax. This would be in replace of our main method. We're going to create an object that extends app. And when we run, an app is going to have a main method in it. App is going to control the main method and set up the whole actor system, set up all the concurrency, set up multiple threads, and do all that good stuff. So we're going to extend app, set some values and some initial code that's going to execute. And then when app runs its main method, it's going to be able to grab our values that we set. We overrode some of its state variables with these values, state values, I guess in this case, and then ran some initialization code. But app is going to control the main. So when we run this, object, we can think of this as our main method, but actually the main is still defined, but it's defined in the app. Anyway, we'll extend app. We're going to create an actor system, which is going to can contain multiple or any number of actors in it, but an actor system is where all of our actors are going to live. And if our actors want to communicate with each other, they should be in the same system. So we're going to create some actor system. We can give this any string. This is just the name of the system, mostly used for, at least for our purposes, for debugging. So when we get an error, it'll say, this is the system name. Actually, we'll only have one system anyway, so we don't need that for debugging. We know what system it came from. Anyway, store that in a variable, and then tell the system, yeah, we're not overriding these values. I've been thinking about that. Why did I say that? These aren't overriding values. These are our own. This is all our stuff. It's not part of the app itself. But the system, we're going to tell that system to create a new actor and add it to the system using this syntax here. This system actor of is going to create a new actor with props. This class is going to create, or object, I guess technically there, is going to create an object of this type. So we want to give it the type itself. We're not saying new, we're not calling a constructor or anything, but we're going to take our actual class, our entire class, give it to props, and put that into the system. So that's going to create an actor of that type and add it to the system. And then that's going to return a reference to the new actor that was created. The app class is in. Let me double check just real quick here. We do not have to define app. I'll say that much for sure. We do not have to define app at all. Oh my goodness. Why did I... Why did I do that? We don't need app at all. Now I'm wondering why I did that. Maybe I thought you had to do it like this at some point. But you actually don't need app at all, apparently. My example in the repo doesn't even use app. So, but no, it's not part of the actor library, or the ACA library. For some reason, I thought you had to set it up like this at one point in time, at the time when I made this slide, apparently. But no, we don't even need to do that. So we could have not extends app and just have this in a main method. Now I'm confusing myself. Why would I ever set it up like that if I don't have to? It's just confusing. I have to update the slide and just use main methods. Yeah, apparently. I mean, this works still, but you don't have to do that. So, but this part definitely is part of ACA, the props and everything that I walked through. But what I want to reiterate with this is that we don't call new on our actors ever. You're never saying new my actor. That's never going to happen. If you're doing that, you're wrong. Technically, you can do it, but your actor is not going to be part of an actor system, so it's not going to behave like an actor. When you add an actor to an actor system, we want it to be able to behave like an actor. We want it to be able to react to messages and everything. If you just say new my actor, your receive method is probably never going to be called, depending on your specific setup. Yeah, why would they name it? Yeah, probably. And I'll get to the message passing part. So we want to create actors like this. And you never say new my actor class or whatever your class name is. We're not calling new, how do we call the constructor? Should be a question on your mind. If we have a value, if we have a constructor in our actor, we can still receive information in our constructor. We can write these like any other class. We can add any context, anything that we could do with a regular class, we can do here, including constructors. In the props, in the call to props, we'll give multiple parameters if there are constructor parameters. So the first argument, if the first argument is always the class that you want to instantiate, then if that class takes constructor parameters, we're going to have comma separated, just more arguments to be able to be those constructor arguments. So here I'm going to create a myActor object with an n of 10 as its constructor call. And if there are multiple parameters in the constructor, I would just keep having comma, more arguments, to be able to add those multiple arguments in there for the constructor call. So let's see an example of this, and I kind of didn't mention it, but this is how we're going to send messages. That's going to be more clear in the example. All of this should be more clear in the example. That's why I have an example, which apparently we're not getting through today. Holy moly. Yeah, the class that you create is going to extend actor. So let's create a few counters which are going to count down from 20 as fast as they can. So let's build this functionality, and I'll walk through this right in the code. Let's look at the code while we talk about this, because most of what we talked about so far is kind of abstract. They're just conceptual things. But let's talk about some code. So here, we're going to create an actor class, which is going to respond to is going to interact with 4 different message types, all of type object, which is going to be start. So these are counters that start at 20 and then count down as fast as they can. So start is going to be the message that they get when they should initially start counting down from 20. An is done message, which is going to be like a question. Is done? Are you done? And when they get an is done message, they're going to respond with either done or not done, whether they've reached 0 or not. So that's we're going to have some code here which except for the extends actor is going to look mostly like a regular class. We're going to give this some name, some string name, just to know which counter this is. We're going to have some variable that's going to be the current count, and some method called countdown, which as long as n is greater than 0, greater than or equal to 0, it's going to count down by 1 and then call itself. So we're going to keep recursively calling countdown until the counter is -1. And if once it's hit its base case, we're just going to print out that it's done and then end the recursion. Now the actor part of this, how are we going to react to each message, that type that's received? When we receive the start message, we're going to set n, whatever its value was, we're going to set it to 20, and then start the countdown. So whenever we receive a message of type start, we're going to execute this code. And I'm omitting the braces just to make it look a little cleaner here, but we could add the braces in too. Whenever I get an is done message, and this is where we're going to talk about our first message that we're sending. This mostly is reacting to messages we talked about so far. But is done, when we receive a message of this type, depending on the value of n, so if n is done, if it's -1, we're done counting, we're going to respond to whoever sent this to us, which we have this convenient method called sender, which is going to have a reference to the actor that sent us the message. In this case, whoever is asking if we're done, we're going to respond to them and send them a message of type done, and we're going to use this exclamation point syntax, which is actually a method. This is a method named exclamation point, and we're going to use the ability that Scala gives us to call methods using infix notation if the method only has a single parameter. So the sender is an actor reference which has a method named exclamation point, which we're going to call using infix notation and send this message, which is just the instance, the reference of the done case object. If we're not done yet, we're going to do the same thing, but send a not done message to respond. Okay, you're asking if I'm done. Let me tell you if I'm done or not. So this is a way we can have two pieces of code running at the same time, but still have them communicate. We have one actor asking another actor a question and then getting a response using these events, which are the messages that we're passing. Yeah, and it does. Yeah, they reuse the not symbol. It is a bit weird. I don't know. I've gotten used to it. I don't see it like that anymore. Hopefully you all get used to it too, but yeah, it is weird at first. So let's create an example where we're going to create a system and create 3 counting actors that I'm going to name. That's why I have this name in the constructor. Give them all names, which is going to, so we can identify each one of them. And then in our main method, in our app in this case, we're going to send each one of them the start message and just let them go. Don't bother, Luke. It's as clear as I can make it. I'm sorry, guys. And all 3 of these should work at the same time. And as we'll see when it comes to concurrency, we don't know which one is going to finish first. We don't know which order anything is going to happen. We're just saying, hey, you 3 things just happen. All of you should happen. So if we go... Actually, I do want to go through this. I'll go through this quickly. We'll... This is the end of it, right? And go over this quickly. I'm also going to create a supervisor actor, which is going to take the references of the other actors. It's fine if this doesn't sink in quite yet. We'll talk about more of this throughout the rest of the week, what this really means. But I'm going to get a list of all of the other actor references and give this references to the 3 counter classes, counter actors that we're creating. And then when I receive an update message, I'm going to send the is done message to each of those actors, and each actor is going to respond with either done or not done. and I'm going to handle those appropriately to check if all the counters are finished counting. I'll go over this slower next time or during Q&A or both. But I just wanted to flash that one so we can see this code run and prove that we actually do have concurrent code running. Oh, and the answer's on the screen. So here we have the supervisor, the counter class, creating 3 of those counters, creating a supervisor with the references to all 3 of them, and then tell all 3 of them to start. And then every half a second, I'm going to tell the supervisor to check in by sending it the update message to check in with each of those actors. So let's run this thing. And here I don't extend app. I just do def main here. I'm still wondering. That must have just be what they did in the documentation the first time I saw it. And for some reason, I just assumed it was how you had to do it. So it's compiling. Let's see what we get here. Actors 1, 2, and 3. Counting down from 20. And what we'll see is that these are, in fact, going to run concurrently. So I'm just printing out where they're all at. They're all saying, hey, 1, I'm at 20, 2, I'm at 20, 3, I'm at 20. And then even though actor 1 was the one that started first, it's actually actor 2 that ends up decrementing first, decrementing to 19, getting all the way down to 16 before the first actor even decrements once. And then 2 decrementing to 15 before 3 even decrements once. And then we just start seeing them intermix. These are running at the same time. They're running concurrently. All 3 of these counters are counting down at the same time. So we actually have no guarantee of which one's going to finish first, of which order they're at. We do get 1 finish first. Well, 3 was at 5 and 2 was at 3. And 3 finishes next. So we get 1, 3, and then 2 is our finishing order. But we have no idea, and there's no guarantee of how that'll actually go down, where they're going to finish, and what's going to happen there. We're just telling all 3 of them to start, and then it's up to a whole bunch of variables to be able to decide what's actually going to be the order, depending on all kinds of different things. How our operating system is allocating CPU time, which core each one of them got, who they're sharing that core with, how the actor system is allocating threads. There's all kinds of things going on to be able to decide that actual order. But eventually they all finish. The supervisor checks in and says, looks like you're all finished.